Here's a quick warm-up question here, a check for prior knowledge. So let's suppose we have two objects of the same shape that are released from rest in the presence of air resistance. Suppose that object 1 has a greater mass than object 2. We want to know which object will hit the ground first. In Unit 1, we saw that both objects will hit the ground at the exact same time due to the fact that the acceleration of gravity acts on both objects equally. However, in this case, we're now considering that there is also air resistance. Okay? So please take a moment to think over your responses and write down an explanation in 1 or 2 sentences in your Bellwork packet. So today we're looking at dissipative forces, the topic of 3.3. What are dissipative forces? All right, well, if you've ever heard of the word dissipate, to make dissipate, or for an object to dissipate its energy, or to dissipate something is to make vanish or disappear. All right, so we'll be looking at forces that make things disappear or vanish. Specifically, what are we making disappear and vanish? So some announcements real quick. We have Unit 3 notes, spell work, and late work, and review will be due Tuesday, November 17th, a Tuesday prior to Thanksgiving break. We'll have our Unit 3 test on Tuesday, 11/17. Okay? Oh, and those are all of our announcements. So what are we up to today? So what are dissipative forces and how do they influence the motion of objects in our everyday life? What factors affect forces such as friction and air resistance? Why is it important to consider such factors? And that's all that we're up to today. So why do we care so much about friction and air resistance? We'll also take a look at that as well. How does it affect on our everyday life? And then we'll also build off of our inquiry activity, our lab investigation, our virtual lab investigation, better said, for friction and air resistance. So the first dissipative force is friction. Okay, so a dissipative force is a force that impedes the motion of an object, a force that attempts to stop the motion of an object. Okay, to dissipate is to make vanish. So a dissipative force is a force that attempts to make the motion of an object vanish and hence stop the motion of our object. So friction acts against the motion of an object. So for example, if we push or attempt to push our crate here to the right, okay, friction will act to the left in the opposite direction. So what causes friction to act against the motion of an object is the roughness of the two surfaces are colliding. Roughness in parentheses. Specifically, what's happening is even though surfaces can seem smooth, okay, if we zoom in real close on these surfaces, like we see happening right here, okay, these surfaces have ridges and bumps and all sorts of unsmooth features to them. So as a result, what's going to happen is if we push our crate to the right here, the ridges from the crate are going to collide with the ridges from the ground. And as a result, the ridges from the ground will apply a force by Newton's third law back on the crate. All right. These forces from each ridge manifest themselves as a force due to friction from the whole entire surface acting on the crate. So there are 3 primary factors that affect the force of friction acting on an object. The first is a normal force. If you recall, the normal force is a measure of the contact between 2 surfaces. Okay. So if you don't have the normal force, if there's no contact between 2 surfaces, there's not going to be any friction. Okay, so for example, if we were to press down more on this box right here, we would make the ridges from the box dig deeper into the ridges of the floor, which is going to increase the contact between the 2 surfaces and result in stronger collisions. And so as a result, the friction is going to increase as we increase the normal force. The materials of each surface, aka the roughness, okay? So each material in the universe has unique properties, such as boiling point, melting point, so on and so forth. One property that we use to quantify the roughness of a surface is what we call the coefficient of friction. And each surface in the universe, each material in the universe has a unique coefficient of friction. And this quantifies basically how rough the surface is, how many ridges are there on the surface, okay? And lastly, similar to the normal force is the surface area and contact. The more contact that occurs, the more collision there will be, and thus the higher force of friction that there will be acting as well. So there are 3 different types of friction, okay, listed from strongest to weakest. There is static friction, which occurs when an object is at rest. The reason why the static friction tends to be strongest at least at the level that we're going to be studying friction, is that static friction is friction acting on objects at rest. By Newton's first law, an object that's at rest will want to stay at rest. So static friction has an additional amount of inertia coming from the box that allows that makes it harder to get the box moving and allows static friction to act at a stronger level than the other types of frictions. Okay. The second type of friction is what we call sliding or kinetic friction. It occurs when an object is moving. Kinetic friction tends to typically be weaker than static friction, although it is stronger in some cases. With the reason being actually the exact same reason as the reason why static friction is so strong, paradoxically enough. So by Newton's first law, once we get an object moving, that object will want to continue to move. So this object already has some inertia that wants to keep it moving. So as a result, it'll be easier to keep that object moving as it will be to get that object moving. So as a result, kinetic friction will be weaker than static. To give you an idea, if you've ever pushed something across the floor or dragged something across the surface, you may notice to get that thing moving is a lot more difficult than to keep it moving, and that's because of the inertia of the object to keep moving once it's moving, thus making kinetic friction weaker than static friction. And again, this isn't the whole story. There are more details in this, but for level what we'll be studying, this suffices. And then lastly, we have rolling friction, which occurs for objects that rotate. Rolling friction is the weakest of the three types of friction, because there's very little surface area in contact with our surface, okay? So a wheel or cylinder like this will only have this one point right here that's in contact with the ground. So there's very little surface area in contact, and thus there's very little friction. So if you've ever noticed, dragging something across the ground is very difficult. An easier thing to do is just to put it on a dolly and roll it across the ground, because the rolling friction is a lot weaker than, say, static or kinetic friction. So why do we need friction? Okay, so it actually turns out, even though we think of friction as a force that stops motion, it actually turns out that if you want to get from any place to another and you don't have like a propeller or anything like that, you actually need friction to move from one place to another. So to illustrate, we'll take a look at two examples right here, okay? Person walking and then a car moving forward, okay? So if a person wants to move to the right, what we do is we push against the ground, okay? So as a result, we're exerting a force due to friction on the ground, all right? And so what happens by Newton's third law is the ground exerts an equal but opposite force due to friction back on us, okay? And this equal but opposite force of friction acts to the right, and it's that force that acting to the right that propels us forward to the right. Now, again, this isn't the whole story. There's actually some misconceptions here, but again, for our level of study, this will suffice, okay? And then the other thing, too, is if you have a car that's heading to the right, what's going to happen is you may notice the car wheel actually rotates clockwise. The reason being is that when the car rotates clockwise, it's going to exert a force of friction to the left on the road. As by Newton's third law, similar to our shoe scenario here, the road will exert an equal but opposite force due to friction on the right, which provides a rightward acting force on the car that propels the car forward, okay? So if we have smooth surfaces like ice or like mud, we're not going to be able to move very much. If you notice you slip on ice or cars can't move in mud because there's very low friction, and thus this exploitation of Newton's third law can't occur. We can't exert a force on mud or on ice because of how smooth it is, so mud can't exert a force back on us. So some other ways you see this is actually the fingerprints on your hands are actually also a biological example of why we have friction. So from the physics perspective, we have fingerprints in order to provide grip and in order so that we can grip onto things via friction. So the second dissipative force is what we call air resistance, okay? Air resistance is similar to friction. It acts opposite direction of motion of an object. In fact, it's actually called air friction by some people, okay? What causes air resistance is that it results from an object colliding with air molecules. So just as there's a roughness of every surface on a microscopic level, there are air molecules that we breathe in. We can't see the air molecules. They're smaller than anything we can make out, but they're there. As you learn in biology and chemistry, we need them to survive. And so what happens is even though these air molecules are extremely tiny, they still exist, so we can still interact with them, they can still bump into us. And so these bumping ins from all the air molecules with an object manifest into air resistance. So for example, an object that's falling like a bowling ball is going to collide with all these air molecules right here, which is going to cause air resistance to push up on our object. and same thing with a feather. Okay, so there are two primary factors that affect air resistance. All right, going back to our beginning of class question here. Okay, so if you drop a feather in a bowling ball in the presence of air resistance, the feather is going to fall at a lot slower rate than the bowling ball. People tend to think this has to do with the mass of the object, okay? That the mass of the feather is so much less than the mass of the bowling ball that the two will drop at different rates. However, what would happen, and this is what we did in class, unfortunately it can't be showcased with virtual learning, is that if you take an object that has the same mass as the bowling ball, or excuse me, if you take an object that has the same mass as the feather, and but has the same size and same surface area as a bowling ball, both those objects will fall at the same time. So what we did in class is we took a golf ball and a sheet of paper and dropped them at the same time and saw that the golf ball hit the ground first. But then we balled up the sheet of paper. If you imagine this as a sheet of paper, we balled up the sheet of paper so that it was in the same shape and same size as the golf ball, and we dropped the two, and they dropped at the exact same rate. So what's actually happening is it's not the mass that affects the amount of air resistance in object encounters, although the mass does play a little bit of effect, but it's not the primary effect, okay? The primary effects are the surface area of the object. So the larger the surface area of object, the more air molecules are going to collide with that object. So when we drop a sheet of paper, it's not the mass that makes it fall slower, but rather the surface area. Because of the surface area of the sheet of paper, or our feather in this case, there's more air molecules colliding with our sheet of paper, which creates more air resistance and thus allows our object to fall at a quicker rate. The second factor is the speed of the object. So the faster an object goes, the more frequently it will collide with air molecules, okay? And you've seen this if you've ever stuck your hand out of a car window or you've ever been on a roller coaster. When the roller coaster starts moving, you feel a little bit of wind past you, but then as the speed picks up on the roller coaster, you'll notice that there's more wind blowing by you and you can hear the wind rippling by you. It's stronger and stronger and stronger. And this is because as the faster an object goes, the more frequently it will collide with air molecules, and thus there's going to be more air resistance encountered. So as a wrap-up, cars are designed to have a smoother surface that results in less of the car's surface coming into contact with wind, in order to make the car more aerodynamic. What factors of air resistance are being considered in the design of this car? Of these cars. Excuse me, that should say car there, not care. Okay? So you can take some time to think about this, but the primary factor is surface area. All right, by designing the car to have less surface area in contact with the air will flow along the car as opposed to colliding with the surface of the car. So there will be less air resistance acting in the car, and thus our car will be more aerodynamic. You'll be able to, what people say, cut through the wind much smoother and much quicker than usual. And this is our lesson on dissipative forces.